First, thank you so much for inviting me here, and also thank you everybody here to listen to this talk. So I'm Jianfeng, and currently I work at the Yale Cryo-EM Resource, and I started cryo-EM work about 16 years ago. It's my great honor to share some of my experience in situ sample preparation here today. So this talk will be divided into three parts. In the first part, I will briefly talk about in situ specimens which can be studied by cryo-EM. And then we will talk about 5 considerations for in situ sample preparation. And after that, I will give a brief tutorial of the major steps of cryolaminar preparation. And at any time, if you have any question, feel free to stop me. And because I cannot see the chart immediately, maybe, so feel free just to speak out.
If anybody has any questions in the chat, I can monitor it and I'll interrupt and ask the question while you're speaking, if that's okay.
Yeah, great, thanks. So generally, if we want to use a cryo-electron microscope to study our biological samples, we need to make sure the signal noise ratio is good enough for us to get the good resolution or good visibility. So generally, the thickness, if lower than or smaller, thinner than 400 nanometer, generally can be studied directly by cryo-electron tomography. The first category of this kind of sample, including, for example, like a virus, like this coronavirus here is around 100 nanometer. And the isolated or reconstituted systems, like here, the ciliary axonine, also a good subject for study by cryo-EM, because this kind of sample have around like a diameter of 220. So you can still get like a good resolution from this kind of samples. And this kind of sample can directly plunge in freezing and imaged by either single particle cryo-EM or cryo-electron tomography. And for thick samples, like the mini cells, which is around like a 400 nanometer. So these kind of samples, you still, even though it's in a age of the capability of cryo-EM, but it still can provide useful information for some stories. For example, here, injectosomes is still studied by Professor Junior's lab. And if you are interested in mammalian cells or samples which grow on the grid, if you look at the peripheral regions, like here, the highlighted in the EM grid, like R2 region, you still can use the cryo-EM to study them. And in this region, if you look at the cross section, this region is still thin enough for you to use either single particle or cryo-electron tomography to study. But for the regions of the inner part, for example, the R1 region, which is really dark, you hardly get useful information directly by cryo-EM. So for thick samples, even like a thicker up to 200 micrometer, in this kind of samples, you need to use other techniques. For example, people in older days will like to use a cryo-sectioning method. So this method uses diamond knife to cut the samples slide by slide, and then mount the samples on the EM grid and transfer it into a symmetric electron microscope to do cryo-electron tomography. These samples is good because the sample still in native or close to native status. However, the cutting process or the technique bring lots of artifacts. So for example, here, as shown in this image, the knife markers or the deformations can be observed in this kind of samples. And nowadays for cryo-EM, many people use like a focused IMB medium. So in this morning, Professor Grant Jackson and Yongxiong already talked much about the lamina. So here I just briefly mentioned that. So this technique uses the focused IMB to remove the material above or underneath of the target and left over only one thin layer less than 400 nanometer. Currently, 100 to 300 nanometer is commonly obtained by this technique. And this kind of sample can transfer into the microscope and done either by single particle or cryo-electron tomography to get the information which you are looking for. And before we introduce the procedure, how to make this kind of sample, we will first talk about the 5 considerations for the in-situ sample preparation. So first, when we try to study a sample, we need to make sure the sample still has the information which we try to get. So first, we need to use some techniques to see or validate the sample quality is still good enough. So most commonly, for example, this is the X-ray samples. Most commonly, we like to use next stain to see the structural preservations. For example, this piece of celiac actins, we still can see the triplet microtubules, and also dyneins, individual dyneins are well preserved in doublet microtubule. And so this is a good indication this sample quality is high. And if you want to ensure or you want to study the motility mechanism, so generally we will still try to add ATP buffer to reactivate the samples. So here, this movie just show that if we incubate the isolated axonal in the ATP buffer, almost all of the ciliary axonal can be activated to generate bleaching. So this kind of samples give us a high confidence that we can get useful information for our story. And the second considerations I would like to talk about is the EM grade selection. So many of you already know the architecture of the cryo-EM grades. So here I will not talk too much details about the architectures of the EM grade. So here just a side view, top view. I want to highlight is that, so if you want to grow samples like a mammalian cells on a grade, it's better to use like gold grade or other material, but avoid the use of copper because copper is toxic for the mammalian cells. But here I will focus more about the selection among the meshes or the whole sizes, because if you look at the scanning image of the cryo-EM grades, and the grid bar actually is very thick. So this kind of thick grid bar, after sample tilting, you will see the block of your view. If your sample will be used for electron tomography, and then this is important consideration for you, because if you select like a small square, like a 400 meshes, and then after tilting to a certain range, for example, in the diagram we show the minus 60 degree to plus 60 degree, only the green regions are accessible by the electron tomography. So this means that if your square is relatively small, and only the center region can be studied. So this will largely limit the samples in your study. So generally for cryo-EAT studies, we also don't like to use like a larger squares, for example, like 100 mesh grid. Those kind of grid, the square is large. However, it's really easy to break up your squares. So 200 or 300 is most commonly used for cryo-electron tomography. If you do single particle using an in-situ sample, I think 300 meshes may be still a good choice. And then now about the hole size. There are many different kinds of hole size. And the people can decide the size for your experiments. If your sample will not do cryo-FIB, but directly imaged in electron microscope, in this case, generally you will select the hole size based on your target. For example, if your target is relatively large, like over near or like 700 nanometer, in this case, maybe the larger square, a larger hole will be better, like R2, R2-1 or R2-2 grades will be better. But if your target is relatively small, then maybe you can consider to use like a smaller hole size, like a 1.2 or even smaller, based on your size. And also the pixel size of your image is also one consideration. If you are aiming at a high resolution, maybe you can use a smaller hole size. And the more carbon will provide intact squares for you to pick up the sample to do the tomography samples. Another consideration here I would like to highlight here is fiducial markers. Even though if you will use a single particle method to study your in-situ sample, like the work of which Professor Yang mentioned this morning, but if you will do it for electron tomography, so fiducial markers still important, because when you do tomography, when you tilt the sample at a different degree, each tilt image, the signal to noise ratio is really low. So in this case, if you can include the fiducial marker like the 10 nanometer BSA gold treated chrono gold, in this case, you can still use these gold particles to align the movie and also align the tilt image at a different tilt angle inside the tilt series. This can significantly improve the alignment accuracy and also improve your final reconstruction resolution. So this is tomography. If your sample will have a signal, will have the fluorescence signals, and then you will use fluorescence microscopy or use the integrated fluorescence microscope to identify the target regions to do the imaging by electron tomography. So in this case, maybe you also include the sample with the magnetic beams, for example, 1 micrometer magnetic beams in your sample. And this will align the fluorescence microscopy images and the scanning EM images to localize the sample and the target region where we want to study. The fourth consideration here I would like to talk about is the cryogen. So the most commonly used cryogen is a liquid ethane. And some people also use liquid propane or the mixture of liquid ethane and propane. No matter which cryogen you use, they have a wide range of the temperature. So for example, the liquid ethane have minus 183 to minus 189. So in this range, we want to make sure the vitrification is completed really well. So in this case, we need to make sure it's in the low end, so not in the high end. So generally, if you use an instrument, for example, you use a Leica LP2, in this case, maybe the instrument can measure the temperature. So maybe give you confidence to prepare a sample in a low or vitrified conditions. But if you use a Witchboard or some other like homemade tools, you need to make sure your cryogen is cold enough. So generally, we will use the ethane ice on the wall of the cups to make sure you see that one, like indicating the temperature is in the low end. In this case, your sample will be vitrified well. Otherwise, maybe your ice will be get a hexagonal ice, like this image show. This kind of sample you cannot use for cryo-EM work. And if your sample are thick, for example, especially for mammalian cells, even though this one example is the yeast cells, for this kind of samples, you will generally need to put some cryoprotectant to ensure the vitrification quality. For example, here, if you didn't put the glycerol, generally you can easily see the crystallized highlighted here. But if you add 55% of glycerol, generally the vitrification can be significantly improved. And here you can see the crystal ice is rarely seen in this kind of sample published in this paper. And similar to other cryo-EM work, we need to make sure every tools which you will use to touch your sample will be cold enough. Otherwise, your warming up of the sample can cause the cubic ice formation. And also for the tools, we need to make sure it's clean, especially, for example, the liquid nitrogen. We want to use a fresh liquid nitrogen. And if it's possible, just wear face masks to avoid the breath to bring the contaminated ice into your samples, like here, this black spot. And the last but not least, in this section, I will briefly introduce a little bit about the plunger. So for in situ sample, a little bit from regular single particle work. Generally, people like to use a Witchboard to frozen samples. But if in situ, generally homemade or like a manual plunger is still a common or popular tools, including many users, including me, like to use this kind of instrument. Because this instrument, we can control the bloating really well to monitor the process, especially if your sample require you to do one-side bloating, and also if your sample concentration is low. In this case, you can try to bloat a sample from the back side. And if you use a manual plunger, you can base on the see the buffer to be brought by the paper to control the process and get the result which you want. And here this is a homemade plunger and good to use. And some companies also provide a commercialized manual plunger. And this even this kind of instrument maybe has lots of need some experience. If you prefer to use an instrument which you use for regular single particle work, you also can use like a EM GB2, Leica, and also VisualBot. And the Gatan's CP3 also good to use. And actually, in this workflow, I will introduce in the third session, I use VisualBot. And in the following part, I will try to use more than around 1 hour to discuss about the major steps of cryolaminar preparation. Before we go into the third part, any questions so far? Okay, good. Yeah, so because I didn't know if there's anything, so every time if you cannot hear me or maybe my internet lost, feel free just let me know.
Okay, you got it.
Yeah. So for cryo-FIB medium, actually now there are several companies who provide instruments for this kind of work. So the JICE, generally cross beam is used in several facilities. But currently, most dominant instruments are still instruments from Thermo Fisher Scientific. For example, here this is a sales is older generation, and nowadays generally some labs, most of the lab already use aqueous, like one or in most of the lab are used two. Some of the lab already get the plasma FIB, like either Hydra or Artis. The Artis is the most advanced instrument for cryolaminar preparation. It has an advantage of, like, for example, like autoloader, you don't need to transfer the sample manually like in other instrument. And also it has a small chamber and also have high quality plasma FIB. However, nowadays, I think Aqueous 2 still maybe the most popular or most widely used instrument in the cryo-EM field. And my experience only limited to cells, so Aqueous 1 and Aqueous 2. So in the following workflow, I will only introduce a workflow using the VisualBot and the Aqueous 2. And because the workflow is relatively complicated, especially for new users. To make a user to easy to follow the steps which are introduced here, I will show the workflow on the left side. And for each individual topics which I introduced here, I will highlight in a blue text, highlight what we are talking about. So, for example, this workflow starting from visualizations, as I mentioned before, I will focus on VisualBot. So, for VisualBot, we still like to use like a one-sided blotting, especially for sample which have a low concentration. I like to use backside blotting. In this case, I will use ACRA or parallel film to replace the field paper in the front side, and only let the backside blot the excessive buffer away from the sample. And after blotting, you plunge the sample into the thing which is cooled by liquid nitrogen. You still can get a really good sample for your cryo-FIB machine experiments. And here I want to highlight that to get a good ice thickness is important for flowing work. If your ice too thick, maybe you will still spend a lot of time to get the lamella. But if too thin, the sample is too dry, so maybe your lamella quality will be affected. So you need some practice to get the thickness which is good for your experiments. Once you get visualified samples, and you can transfer the sample into the cryo-FIB machine, like a Aqueous 2. But before that, we need to do some preparation work. First, we want to prepare the Aqueous 2 and then prepare the grids. I will introduce the details later. And after this kind of preparation work, we can transfer the grids into the Aqueous 2 machine. Before we introduce the preparation of the instrument. Here, I want to briefly talk about the computers of the R+2. In most facilities, the R+2 is configured with two computers, the supported PC and the R+2 PC. The supported PC have a software which you can control the nitrogen gas, which is used to cool down the cryo stage where you put the sample. And another advantage of a supported PC is that it has internet access. So it means that after you loading a sample into the machine, you can do many steps remotely at home using the remote software. And in another computer, like an R+2 computer, because this one, for safety concern, generally there is no internet access, but it has all the softwares which are used for your laminar preparation. And in this workflow, I will introduce the 4 software. And in each step, which software is used, I will highlight. And for the beginners, maybe you will feel confused by so many softwares. But after some practice or some usage, you will feel actually really straightforward because the workflow also relatively simple. Before you prepare the instrument, first you need to select the throttle for your instrument. For the instrument which has the integrated fluorescence microscope in your system, generally we will select the auto-grid throttle 35, this one. And after we select this one, we can move on to purge our systems. The systems is using the gas lines. So if the microscope is running, generally the sample stage is cooled by nitrogen gas, which is cooled by liquid nitrogen from the dewar. But before use, you want to make sure the pipes are dry and clean, especially if the instrument is idle for like a week or months, not frequently used. Generally, you will purge the lines with the dry and warm nitrogen gas to keep it dry and warm. And also similarly, you also will purge the cryo station, which you will try to load the sample into or outside from the cryo-FIB machine. And generally, half an hour is enough. In addition to purge the gas lines, you will also purge the sputtering lines and also the gas lines. For example, here, this is use the sputter panel to coating the samples. So we will also use the argon line to purge the argon line. So we will transfer the condition to the sputter vacuum and the purge for several cycles. And after that, we will also purge the gas system. Generally, 2 minutes is quite enough for keep the system clean and dry. And after that, we can start to cool down the system. Generally, in the very beginning, if you want to speed up the cooling efficiency, so you will try to use a higher speed. For example, 190 is the one speed which is suggested by some official scientific. And after the cryo stage cool down to like minus 170 or even better, like a minus 180, you can decrease the flow rate to like a lower number, for example, 165 here. And but of course, different instrument, you will use a different flow rate. And we like to use a low flow rate if the low flow rate already can maintain the low temperature because your dewar is a limited size. If you use the original version provided by Thermo Fisher, you want to make sure if you want to do the milling overnight, the liquid nitrogen inside is enough for the work. So in this case, we will try to use a low flow rate, which is still enough to maintain the low temperature. But if you use the system, for example, from Nanosoft or from other companies, maybe this is not your concern. And you just need to find the number which is good to maintain the cold temperature of your system. And during the cooling down, you can use the time to keep in your grid if your grid has not clipped yet. So the loading station provided by thermal fissure. You can use it to clip. But even though this is not a really high efficient, but you still it's enough because you only need a 1 or 2 grid clipper here. So you clip the grids. But here I want to highlight the details about the orientations of your grid. First, you want to make sure your sample is facing up. So if you look at the schematic image, the left image is the conventional auto grid. The right image is for a FIB auto grid, which is designed for cryo-FIB. It compared to the conventional auto grid, it has a low, like a milling slot, which provide like a lower edge. So enable you to use a lower milling angle and get a longer lamella. So which is good. Another advantage is that there are additional marker on the grid, so easy for you to orientate your grid. But no matter which grid you are using, you want to make sure your sample where you glow, for example, the vitrified cell, the cell is here, is facing up towards the back side of the auto grid. Otherwise, the milling cannot be carried out efficiently if you glow cell on this side. And in addition to the marker which is provided by the auto grid, we will add additional marker. For example, here we were in the side rim of the grids to make a marker here. This is really important for us to rotate the grid later when you transfer the grid into the cassette and transfer into the electron microscope to do the cryo-electron tomography or cryo-EM. This is important because we want to make sure the axis of the lamella is perpendicular to the tilt axis. And I will show the importance later. But at least here, I just want to highlight that you make a marker on one side of the here, for example, here. Once you transfer this grid onto the box, this side will on the top, and then you can use this marker to rotate at 90 degrees, and then transfer this one into the cassette. And this will ensure the lamellar axis is perpendicular to the tilt axis. So the importance is shown here. So if it's perpendicular, this will avoid the blocking of the neighboring features, block your view of the recorded area. Especially if you're collecting tomography data like tilted samples. Another advantage for this orientation is that when we do focusing, if you focus area is along the tilt axis, so the good orientation will ensure the same z-height of the focus compared to the R if you look at the cross section. But if the orientation is bad, the focus area actually, let's say, is different from the record. So for example, here is higher than the record. And the bad situation is that after tilting to different angle, the area is different. So this will make your data based on the focus area to get the focus of your image is not accurate and different inside your tilted series. This is not good for high resolution data. So that's why we want to make these markers. And after that, when we are clipping the grids, we can transfer the sample into the cryo-FIB. So we use the transfer rod to load the strato into the system. And here, this is a photo of the strato. So once we put the auto grid into here, the median slot will help us to fine-tune the location. So here you will try to rotate the grid to make sure that the median slot facing upwards, and then you lock the location of the grid relative to the strato, and then transfer into the transfer rod. So you will release the lock, tilt 90 degrees, and the strato can be loaded into the transfer rod through its grab tip. So this tip has a needle will insert here and grab this into the chamber. This is loaded into the transfer rod. And here you will see this transfer rod have a chamber inside here After you transfer the sample into this chamber, you can close this valve and pump the inner side of the chamber. This will provide a vacuum good enough to maintain the temperature and also the cleanness of your straddle for several minutes, which will provide enough time for you to transfer the sample into the cryo-FIB machine like Aqueous 2. So this movie is a show, I will turn off the sound. So this movie is recorded by my previous colleague in Czech Republic in the factory of the Aqueous 2. So it records the details of the transfer process. So first, you will put the transfer rod here, and before you open the valve, you want to make sure this chamber is clean and dry. So first, it will pump the lower part for a while, like 10 or 15 seconds. After this pumping, this valve, the bottom part, there is a valve, you will open it, and then we'll purge it, and then open it. And open this valve, and you vented the dry nitrogen gas will fill up the chamber. And then you can lower down the transfer rod to pick up your straddle, and then pick up and then secure in the top. And then close the valve at the bottom, and then pump the chamber in the bottom part for around 15 seconds. This process will provide a vacuum which is good to maintain the sample inside the chamber to be cold and clean. When the pumping is ready, close the top part of the valve, and then vent the bottom part. After vent, the top part can be easily to take out and transfer into the Aqueous 2 machine. And you lock it, secure the transfer rod. After you press the P, the system will move the sample stage to the location where it's ready for you to transfer the sample. And then here, the air lock will be pumped. Once the vacuum is ready, you will hear a sound, and then you open the valve and transfer the sample into the chamber, and release the sample and transfer the transfer load back. You can keep the transfer load here because if the sample is not good, you can immediately pick up the sample and try to change another batch of samples. But if it's good, you still can keep the transfer load here to keep it like in vacuum conditions. When the lamella is finished, you still can pick up the sample and back. After you transfer your sample into the cryo-FIB machine, now you can quickly take a low magnification images to evaluate, like a quicker screening, to evaluate if the grid is good enough for you to continue the experiments. So generally, you will turn on the electron beam, and we'll focus the image and to link the Z hat. In the very beginning, before link the Z hat, so here the Z value is counting from the home position to the surface of your sample. This position is not good for you to move around the stage. So generally, we will focus the image and then link the Z. After link the Z, the number will count from the poppies of the electron beam. And the distance will change from the electron beam to the surface of your sample. And this distance will enable you to accurately and also safely to move your sample around the location where you want to do the flowing experiments. And we will decrease, we will select a magnification, which is good to take an overview of your samples. You don't want to spend too much dose on this sample, so you will try to use like a relatively low resolution, but it's still good enough to draw a conclusion if this sample is good or bad. And you can take an image of it one by one, and then you move the sample to the mapping position and take the image one by one and evaluate. If the sample is good enough, you can proceed with the next step using the map to generate a high-quality atlas image of the grid. But if not, you can immediately transfer the sample out. The tool is still there, the loading station is still called, you still can transfer another batch of sample to continue the work. If the grid is good, now you can start the map software and create a project. And acquire, first you will either import the image from previous image into this software or just take a snapshot. And you use this snapshot of the entire grid to generate a tile template. So this one is, we want to use the higher magnification and a higher quality image to generate the atlas of a grid, because we want to, based on this image, to localize the location where we want to add the position to do cryo-FIB milling to get our cryo-FIB. So generally, this software is really good to use, really a little bit similar to Photoshop. You can create a folder for individual grid. And then inside this folder, you can try to create individual layer. For example, in the tile of the atlas. And then later on, if you add individual lamella location, you will have a position. For example, like here, you can add an individual location for individual lamella site. Once you get the position of the lamella, you also can move forward if you have a integrated fluorescence microscope column inside your system. So Aqueous 2 generally provide this configuration integrated fluorescence. It have a object length, even though only 20 times of magnification and the view only like several hundred micrometer, but it's still good enough for you to find the packet which you want to image. So, for example, here, if your sample have a magnetic beads introduced before, you can use fluorescence signals to correlate it to your scanning EM images to find the target location. If you don't have a magnetic beads in your sample, you still can try to cut the markers. So, for example, in this image show here, you can use the refraction image to detect the location of your fiducial, which you use IMP to cut. And then later on, you will also acquire the fluorescence images. The advantage of this system is that it will not provide the image in XY, but also allows you to acquire a stack of the images. So from the stack, provide some information from the Z and help you to, based on the guidance of the fiducial marker, and to localize the region of the FIB median locations. I will introduce the example later in the following slides. So if you decided to use fluorescence, first you will move your grid into the mapping position and just open another software like fluorescence microscope control. And this software enable you to, for example, switch from you just click LM, and the software will move the stage to the location where enable you to use the light microscope to visualize your samples. And you can adjust the parameters and get a good focus. After you get a good focus, you can save the focus location, like I said, the focus position, and later you can go back to this location, just hit the go to focus position. And this is the refreshing images. You can tune the parameters like exposure time and the intensity to get the signal which is good for your experiments. You also can tune the parameters for the fluorescence if your sample have the signals. And then you can acquire the reflection images and the fluorescence images simultaneously, and for a stack and from different J hat. For example, you can set up a starting J hat and in the J hat, and then you can acquire a stack. For example, you can pick up how many pieces or slices you can acquire, and the list will even though the accuracy is not like a very small, but at least provide some choice for you to position along the thickness of your sample. After you get the fluorescence images, you can transfer this image into the map and align the fluorescence image with your scanning EM images and localize the targeted features. So this is an example we use a fine-tune, just manually move the image into align the scanning images. Sometimes you also, if there's distortion, you also can use multiple point alignments to just find those three features in the EM image and the fluorescence image and align them well and get this kind of localization. And this one will tell us which cell has the signals and which cell has no signals, which you are aiming at. And then you can pick up the location to add the lamella. And the stack information really useful for you to add the fiducial marker and also at the point region of interest in the map software. So you can try to find the focus and find the slice where you can get a good contrast and add the fiducial marker and also add the region of interest. And this information later will be used in AutoTem to localize the lamella samples. And before we started to do the milling, use the AutoTem software, generally the sample is not good enough. You need to provide some, you need to prepare a sample. Like, for example, the first thing is that we will try to coat the sample with a thin layer of the planet. So this is important for some samples if the charging is an issue. So we will coat a thing like a 1 or 2 nanometer pattern on the surface of the sample. For example, in the left image, you see the charging will affect the identification of the sample or localization of your sample. And also during the milling process, if the charging is issue, will cause the drifting. So if you put a layer of a planet, also can significantly address the charging issue. So that's why most of the people, even though here we mentioned that it's optional, but most of the people will try to coat in one layer of the planet. And this is achieved in the software, and you just pick up the parameter, for example, 30 milliamp and the 10 puck, and select the time. 15 seconds is quite enough, and then you will run the procedure. This video is recorded by, I will show a video recorded by Samuel Fisher. But before you do this, generally because the procedure will temporarily increase the temperature of the sample. So to ensure the sample temperature is not affected much, we will temporarily also increase the flow rate of the poured nitrogen gas. So for example, before if my rate is 165, here I will increase to 210, and this will maintain a low temperature. So this video we will see once we start the procedure, the instrument will move the stage to a location where it's good for the sputtering. And before the sputtering, the strutter will block the poppies to protect the poppies, and then move the stage to the sput tube, which is inserted here already. And the sputtering will do several cycles, and you will wait until it's finished. When it's done, the tube will be retracted, and the sample stage will move back to the location where you want to do the next step. And the strutter will be also retracted. So this strutter is retracted, and the tube, the sample move away, and now it's safe for the tube to be retracted. And then the sample will move back to the location for next experiments. So after that, the sample still not ready yet. Now we will deposit another layer of a planet. So the this layer of planet is important for the milling because this dense or layer of planet is dense and focused in a region where in a grade which we want to mill. And for your for sputtering, we will do the sputtering for both grades. But for the GIS, generally we can pick up a different parameter for different grades. And once we have this layer, you will get the protection from the planet layer. And later on, you will get high quality of the planet. If the planet is not enough, for example, if you look at the image here, the left image shows the planet layer here is still intact. We get a high quality of lamella. If you keep on milling the sample for a while, if the planet disappears, for example, on the left side, you can immediately see the sample will be damaged very quickly. And also you will see the curtaining. So here you will see the straight line is the curtaining. So the planet layer will significantly reduce the planet, the curtaining, and also will reduce the repetition issues. So it's important for the quality. So this is the most critical parameters you will play with when you prepare your lamella. You can, based on your sample, to increase or decrease the time of the deposition to make sure the planet layer is thick enough for your sample. And after that, some people can go directly to milling. But if you're concerned about the drifting or concerned about the charging, you still can add another layer of a planet, just similar to previous round. But this is an option. Some people do it, some people just skip. And after these steps, we are ready to decrease the flow rate of the nitrogen to make sure the using of the nitrogen will be not too fast and still good enough to maintain the temperature of your sample in vitrification status. After that, we can start to use the focused ion beam to mill the samples. So here, generally, the AutoTem is a really powerful software provided by Thermo Fisher Scientific. The company already uses some samples. For example, use the mammalian cell and N9 cell to make a lot of tests and use the test results to create a template. And a template already including all the steps of which is required for a milling, starting from the preparation to the end of the polishing. For example, here you will see. So when you load the sample into the system, you want to make sure you can use the scanning EM to visualize your sample and localize the location where you want to look. And later on, you based on this guidance to put a pattern and use the pattern to mill the sample. So we need to make sure the sample is at a U-centric height. So means that when you use the scanning EM or use the focused ion beam to visualize the sample that at the same location, even though in reality there are a little bit of small offset, but you still can make the offset very small enough to look at it in the same view of your image. And another thing important is that you also need to determine how many degree you need to tilt your sample to enable the focused ion beam to mill your samples. For example, here this image shows 9 degrees between the milling angle. That is between the grid and the focused ion beam. And we generally like to use a smaller angle compared to larger angle because the smaller angle, the lamella on your sample will small, and when you do tomography, if you do 60 to 60 degree, this one will, because our stage have a limit like a minus 70 degree to plus 70 degree. If you have an additional tilt angle here, and then you need to limit the highest angle for your electron tomography collection. So that is one thing we want to use small tilt angle as milling angle. Another thing is that if you use like a large milling angle, your lamella will maybe relatively short, so relatively difficult to get a long lamella, which provide enough area for your experiments. And all these steps can be automatically did in the software. So you just set up the parameters, and the software will do it by themselves automatically. Another thing here is highlighted here is the artificial features. This one is optional. Generally, people don't need it and also exclude it. But sometimes, if your sample is relatively featureless, so difficult to monitor the procedure or find the regions. So in this case, you can try to manually add some features here, just like a list of features to increase the features to enable the identification of the locations. But in most of the protocol, maybe you don't need it. You just use it as needed. One important thing in this part is that the software will also provide the choice for you to cut the stress relief cut. So this is originally introduced to the workflow by Dr. Wolf and his colleagues in 2019. And in this paper, they call macro expansion joints. And it's really useful to release the pressure during the milling. If you didn't cut this one, the pressure of the tension will squeeze the sample and make the lamella bend. And if the lamella is bent, and it's really difficult for you to get a really thin lamella, the pattern will cut your lamella away, so break up your lamella. So this one is really useful for high quality lamella, especially if you are aiming at a wide, like more than 10 micrometer lamella, and generally this is not needed. And for the medium, and in the previous slide, even though I show you that you use the focus amping to cut the top part and cut the bottom part to get the thin lamella. But in reality, we need to balance between the throughput of the medium and the damage of the medium. Because if we want to speed up, for example, when we cut here, the big chunk, the big amount of the material above and underneath, we need to make sure the speed is fast. Otherwise, if you use low current, it will take forever or take a long time, which is not what you want. So we will use a high current, for example, like 0.3 or 0.1 nanoamp, and to mill the samples. But this high current will induce lots of damage on the surface. In this case, we will try to cut a thick lamella, for example, 2.5 micrometer. So this one is still far away from our target, which in the inner part, in the center part. So we don't need to worry too much about the damage of your target. And once we remove a big amount of material, we can try to use a lower current, for example, like a 0.5 or 0.3 picoamp. Most of commonly used is like a 0.5 nanoamp, and 0.15 picoamp. And then you can try to cut thinner lamella. And these steps by steps will handle like a good balance between throughput and the damage, and give you a workflow which is really efficient and really minimize those damage in your lamella samples. So the software also have these parameters available. You just set up the parameter, and generally the parameter provided by the thermal feature is good enough for most of the work. But you can fine tune the parameters based on your need. And finally, you can also save this template for your future experiments. Once you get the list template and modify the template based on your need, you can save it and load the template and then start the milling process. So first, you still want to do the preparation, because after the preparation steps, you can try to position or refine the position of the lamella, which you added in the map software. So once you create a project and transfer the live project from the map into the auto 10, it automatically load the laminar position here. And if you start the preparation, it will try to do the eccentric height and also try to find the meeting angle for you. And after that, after you finish the preparation for all the lamina, you can go to one by one and try to refine the position. So for example, you pick up one and just drag the fiducial marker, which is highlighted in red mark here. So you drag this one to the fiducial marker. And the region of interest which you add in the map software will automatically drag to the location along with the fiducial marker to the location, which should be the location is a signal which you have. For example, if you use fluorescence microscope, they're called integrated microscopy images to localize your target. And this one will provide some localization for the Z height, so enable you to put the lamina. And then you can tune the parameters based on your need, try to find the location to do the milling process. So you will do one by one. And when you finish it, you can start to do the milling. And during the milling, you also can change the parameters based on your need. For here, individual one, if you not started yet, you just try to open it and change the parameter, and then the change will be used and to milling the samples. And each lamina, the time will estimate based on the parameter which you choose. And this time will provide some estimation for you. If you feel comfortable to do both the milling and the thinning, you can check the thinning here. And the next day, after the overnight milling, you can come back to collecting your sample and transfer the sample either into the microscope or to storage tank to further use. But if you feel uncomfortable to leave the sample in the cryo-FIB machine, especially because the current cryo-FIB machine, even though the vacuum is good, but it's still not good enough to keep to avoid the ice contamination. Along the time, more and more material or ice will accumulate on the thin layer of lamina. You don't want the fine polishing lamina, which is like 100 or 200 nanometer thickness, stay in your chamber for more than 2 hours or 3 hours, which increase like a 20 or 30 nanometer additional ice contamination or deposition of the material. So in this case, you also can try to specify the delay time or just do the thinning in the next step for your experiment and come to lab and then collecting the sample and to get the sample for your work. And this is just to show you one example of the final result which we obtained. So this is a cross-section view using the M-beam to take one image. So this is thin lamina and the pressure relief cut is here. And during the process, you also can use the scanning EM to take one image. But in the end, if you don't concern about those damage, you also can increase the resolution or dwell time to improve the resolution. But if your sample will be used for like a high quality tomography imaging or single particle, I will suggest you just try to minimize this kind of exposure because every image will use those and cause damage, especially the current here, especially the voltage is low, so the radiation damage is relatively significant if that is concern for your high resolution. And this is another example which I take several years ago, and this is the sample. So here, individual is the sample maybe really small, so difficult to get a high quality lamina. For this kind of small samples, you like to get an aggregation and like here aggregation like many is the cells, and then you can cut to get like a lamina is larger than 1 micrometer. So here, this is the IMB images, this is electron beam images. And in these images, you can see, even though here you will see a little bit of feature, but it's still not good enough for you to study. This is not a volume work. And here you see the black spot just inside your sample, the material is different. That is also another example that the planning is important to make sure the curtaining caused by different dense of the samples. The third lamellar example, which I show here, also is the samples. Here, just take a movie to show the procedure of the medium. And this movie is took 30 times to speed up, so you will see the process. So first, this is a pattern of the stress relief. So it really quickly, because it uses really high current. And after that, you will cut the top part and the bottom part use a high current like 0.3 nanoamp, and remove the top part and the bottom part very quickly. And after that, you will make the pattern a little bit narrow, and also to make the distance between the two patterns a little bit narrow to get a thinner lamella. And also use the lower current, for example, decrease from 0.3 to 0.1, or even like only 50 picoamp to get like a little bit slower medium speed, because this time you only cut a small region, not like previously like a small large region. So this was still enough, maybe only 5 or 10 minutes to finish the second medium, and then you just step by step, and then in total 1 lamella, maybe less than 1 hour, you can get the 1 lamella prepared. And during the process, you can also try to take the scanning image to monitor the process.
Oh, we have a quick question. Did you
Yeah.
mean contamination can accumulate 20 to 30 nanometers in a couple of hours?
And that I didn't know. We even though I mentioned 20 or 30, that is a little bit not a reality. I didn't try to measure, but at least just roughly say along the time. Every instrument have some SAT result that will give you information along the time how much ice contamination will accumulate on your surface. So that is one information you can look into. Another thing is that because SAT, maybe the result is different from your experiments conditions. So a good example is that after you get a sample, you also can do the tomography. And if you see, because in the tomography, you can see the cross section, and in the cross section, you also can try to, based on that information, to see how much ice is accumulated on the surface of the lamella. And also look back to the time you wait there, and then based on that one to make a judgment. But the longer is not good. I didn't calculate the time, but at least as far as I know, people feel uncomfortable to keep the lamella there for more than 4 hours. Yeah. So here you will see these lamella images. Actually, this image, if you compare to previous image, not like high resolution, just because the image which I use here is low current and shorter dwell time. Actually, this lamella is really high quality. So after you get the high quality lamella, it's not a guarantee your target is still there, especially if you are picky about the location. If you use a fluorescence to localize your location, and then now you can use the integrated fluorescence light microscopy images again to double check if the feature is there. For example, if you acquire like a 20 or 30 lamella one night, now you can go back to use the integrated fluorescence microscopy to see if the feature is there. For example, here we just see, even though this is thickness around 150 nanometer, you still can see the green signals on your lamella. And this one will help you to pick up to the lamella which you want to collect in tomography. But a little bit time consuming because efficiency is relatively low. So if you use fluorescence, generally you cannot guarantee to get many lamella in one night. hopefully the artist can provide a higher throughput, or future instrument can provide a higher throughput. And after that, generally people like to code another layer of panel, because this is very important, especially if you will collecting data using a faceplate. After the medium, different from regular cryo-EM samples, which have like a material connected to your sample, the conductivity is very good. But now your lamella like a bridge, only connected to the neighboring area through the two ends of your material connecting to your lamella. So the conductivity can significantly reduced. So in this case, people will try to add additional layer of a planet. So this layer planet actually will also add background to your samples. If you add like before, still use 30 milliamp and use 30 and also use 15 seconds, and that is not good for your thickness of your planet layer, because later you will see really black or really dark background for your data. So you need to fine tune. If you're concerned about it, you need to decrease the parameter to get the result, which is good for the conductivity and also not too much background. But for starter point, it's good just to use a half condition of the one which you used before. And if you don't have the charging concern, for example, if you skip it and did not have any trouble, you also can skip it. Like many users also skip these steps and still get a good results. So now after you get the good lamella, now it's ready for you to transfer the sample from the cryo-FIB machine out. And so this transfer rod still packed on the cryo-FIB machine, because here is still vacuum, so your transfer rod is still clean and dry. So now you just press the button. I will press the movie, and then you can see the. So you first press the P button. So it will move the sample to the location where ready for you to pick up, and also pump the air lock. And after pumping again, now you are ready to open a valve and also release the transfer rod, slide in, and pick up your throttle and lock it and retract it. And secure, because the vacuum will drag the load back, so you need to secure it. And then close the valve, and then close the chamber of the Aqueous 2. And then you will vent it, because here you need to make sure the vacuum is good enough. Vent it, and then you can release the transfer rod and move the transfer rod to the loading station. And before you open the valve, you still will pump the bottom part of the valve, because you don't want the moisture inside it goes into your chamber where your sample it is. And when the pumping is ready, the light will flash quickly and remind you it's ready, and then you can vent. Open the valve and vent. After vent, the nitrogen gas will fill up the chamber to keep the chamber like a moisture free. Even the short time of warm nitrogen gas will not affect your sample, because your sample is protected by a throttle, still clean and dry and cold. And then you transfer the sample back to the loading station, and now your sample is in liquid nitrogen. It's safe and clean. And you will still pump the load transfer rod for a while, because you want to keep this rod clean for next usage. And then this is all done. So after this, you can transfer your sample to the transmission electron microscope. For example, the cryo, to collecting single particle, either like in situ single particle data, or just to do electron tomography work. And as mentioned before, the marker will help you to rotate the grid 90 degrees. This is needed for the current version of Aqueous 2 Aqueous 1. And for artists, if you use specially designed grids, and then this may be not needed. And the workflow which I introduced on the left side is a complete workflow. You have many steps. And this is used for the example which I show in this talk, Laminar 4. And in reality, you also can change the sequence based on your need. For example, if you don't have a difficulty to identify your location to put the laminar sample, for example, for yeast or some cells, in this case, you also can do the sputtering and the GIS in deposition first before you use a fluorescence microscope to identify the signals. This kind of sputtering or deposition will not largely affect your signal of your fluorescence, especially if your fluorescence signal is strong. So you can try to do this kind of thing to protect your sample first and then do the fluorescence steps. And then this is used for my laminar sample 1, which is shown in previous slides. And for some system, if you don't have integrated fluorescence microscope tube in your system, or if your sample does not have fluorescence signals. So in this case, you can skip this one, will speed up your meeting, and then throughput will significantly increase. So this is this method show up. And if charging is not an issue for you, you also can try to skip this the second step of PT sputtering and even the last step of PT sputtering. So this will make the workflow really simple. You just screen the result, the grid, and then do the sputtering, and then do the GIS deposition, and then do the milling. And one night you can get 30 or 40 lamina easily if your parameter is well defined, and then get the sample and good for you. So for example, is the sample which I show in laminar 2 and 3 use this method. And after introduce the workflow, I would like to use the movie from Thermo Fisher. Most of you already see this morning. Professor Grant Jackson also show this movie. So here I just want to kind of like a little bit summarize of the procedures which we showed before, but this procedure actually is not identical to the procedure which I introduced. Some steps are skipped, or some steps are simplified to demo the steps. But it's 3D and easy and very easy for you to understand. So this is a chamber, it's really large. So let us include in artists, make it really small. It's really good for the high vacuum and the cleanness of the sample. So you transfer the sample into the loading station, which is cooled by the nitrogen gas. And after that, even though here it does not show the platinum sputtering in the first step, but here show the needle of the GIS inserted and do the GIS platinum level deposition. And after that, you use electron beam to identify the location, and then use the ion beam to position the pattern where you want to cut. So in this video, it does not show the stepwise milling, just show the pattern from the top and the bottom, and because it's a focus ion beam, so it's milling from one line, just from one side to one side, not like a pattern, whole pattern gone. It's doing very quick, so that's why looks like a whole pattern gone, but actually it's scanning just from one side to one side. And in reality, actually like a stepwise from like a high current and like a thicker lamella, and then step down use the lower current and the thinner lamella. And here just use the highlight, the platinum layer. This is like a really, really important for the quality of your results. Many people get a poor result because the GIS layer is not a good quality, especially in older version when we use cells or use Aquarius 1, we need to manually find the position which is good to the GIS. But now Aquarius 2, the predefined position, generally you use the default setting, you can get a really good layer of the GIS. And after that, you also do the platinum to increase the conductivity, and then you transfer the sample into the transmission electron microscope, the holder, and tilt the sample to acquire tilt series image for cryo-electron tomography work, or just do in situ work, which described introduced this morning by Professor Yang. Okay, this is our movie. And last but not least, I would like to thank Professor Julian in Yale and also Professor Chen Xu in UMass Chan Medical School, because I use their instrument for refreshing my memory of the instrument and thus to refresh my skills. And during this time, I also get a lot of support from Han Kang Shou. In that time, she worked with Chen and UMass Medical School, and then now just recently joined Yale, become one member of our team. Yeah, now I'm happy to take questions if you have.
We have one question in the chat, a follow-up from Guobin's initial question. Guobin was asking if the factory has a specification for the contamination rate.
Oh, sorry, could you repeat again?
Guobin, maybe you could ask.
Oh yeah, so I'm curious if there's any specification for the contamination rate for I-2.
I only remember that in SAT they provide information about the contamination rate. So when you sign off, there is information. And the engineer also provided some information, but a long time ago I forgot the exact number. But in reality, I also, when I do my experiment, I also curious the thickness. I also pay attention. I do cryo-electron tomography and then look at the cross section and give myself some idea how severe the ice contamination will be.
Okay. So yeah, if I heard correctly, you mentioned 20-30 nanometer in a couple of hours.
So again, I don't want to mislead you. I just try to say a number which just say we don't like to keep the sample in the chamber, which I vacuum is not good. Not like in autoloader. Even in autoloader, the vacuum is far better. We still concerned about the contamination. So if we didn't use the microscope, if the sample still in autoloader, we still turn on the turbo pump. But now, if the sample in the chamber vacuum, even though it's high, but compared to autoloader, is not good. So we feel uncomfortable. So we always try to minimize the time to let the sample stay in the chamber. And another thing is that generally people like to the software will put the location in the home position, which is far away from the top piece of the ion beam. That is also better because that location is more clean, because the location close to the ion beam maybe have more contaminations. So it's not good for your sample.